So in this example, we're doing exam review 3, question number 9. We're told that we have a toroidal solenoid, so which is basically a donut solenoid. So we have, here's our donut. Okay, so here's our donut, and actually, upside down, but it doesn't matter. So we have a wire wrapping around this donut, and I will go through it. So it's wrapping around, connected to a battery, and we're told that the number of windings, so I'll do a cross section, we're told that that top section view, so here's our donut, and we're told that the radius of the donut R is given by 1.2 meters, big donut, and it's the current carrying wire, right, has a current value of 3.4 amps. So standard unit, so I won't even bother putting it in. And then we're told that the number of windings per meter, so N, is 3,400 windings per meter. So windings is not a number, so I'll just say divided by meters. Windings per meter. Okay, so the question is find the magnetic field B along this. So the first thing you should notice is that the magnetic field strength should be symmetrical along the center of that donut. So I can use Ampere's law in the first version I gave you, where if you're given some path and the magnetic field is uniform along this path, constant value, then B times the perimeter length is equal to the current that is proportional to the current that punctures the surface. So there might be different points on the surface where current is puncturing right through that surface, delimited by this perimeter. So that's given by mu O times I, the current that punctures it. So in this case, right, we know that this Ampere's law basically says we have B, which I'm trying to find. What is the length of this perimeter? So the perimeter is a circle. It's the perimeter, the perimeter of a circle, which is times the length of 2 pi r. And that's equal to mu O times the current that punctures the surface. So again, remember that when I look at this disk corresponding to the circle, right? So here's our disk. There's some windings. There's winding. Wire is like going in and puncturing that surface. And so the current that's punctured, right? The number of these punctures, right, is given by N times 2 pi r. So N is the number of windings over the length, so the number of punctures that we have inside this circular radius, right? I'm sorry, this disk, right, is going to be N, the windings per meter, times the length of that perimeter. So, and then each of those windings, right, so this is the number of times you have punctured that disk. And then you have the amount of current that punctures is times I, because the current is coming out of the board. So this is really N times 2 pi r times I. I'll put the I outside. I. And so we can actually cross out the 2 pi r and say that mu is equal to mu O times N times I. In this case, mu O happens to be 4 pi, so times 10 to the minus 7. The number of windings happens to be 3,400 windings per meter, and the circumference the amount of current that's puncturing each of those punctured is 3.4 amps. And so this is the final answer. I won't plug this into a calculator, that's just a numerical work. So whatever the answer is, it's in Tesla, so I'll put a big T in there so that you understand it's Tesla. So this is the magnetic field inside a toroid.